Welcome to our super fast video lecture on strong acids and bases, topic 8.4. Our essential idea is that the pH of an acid or a base depends on the concentration of the solution. The strength of it depends on this idea of dissociation. How much do these pieces and parts pop apart? HCl can dissociate into H pluses and Cl minuses. That dissociation or ionization of our acids is what makes our acids and bases strong or not strong. Our objectives for today, we're going to define strong and weak acids and bases, explain the strength of acid with Ka, which is a lot like Kc. Remember, that's our ratio of product to reactant. We're going to understand that strong acids have weak conjugate bases. We're going to distinguish between weak and dilute acids and bases. Then we're going to describe methods for determining if an acid is strong or weak. So first up, let's remind ourselves what even is dissociation. So sulfuric acid here is a strong acid. It is going to almost completely dissociate when it's dissolved in water. So we're going to have mostly in our solution H pluses separate from HSO4 minuses. Only a few of these guys, H2SO4s, are going to stay stuck together in our solution. They're mostly going to pop apart. We can quantify that with dissociation constants. So this A here is for acid. So it's the acid dissociation constant. And we're going to look at the ratio of hydrogen ions that have popped off the acids, and then whatever anion is left, the ratio of those guys to the full acid unit still stuck together. We can think about these guys as the reactant and the products, just like we would think about that ratio with our Kcs, our equilibrium expressions. We have products on the top. In this case, the products are the ions, and then the full unit of the acid or the base on the bottom. Looking at the equilibrium constants, dissociation constants for these strong acids. These are strong acids. Notice that they are much, much, much greater than 1. And when we have much, much greater than 1, equilibrium constants or dissociation constants, it's because we have way more product and a tiny little bit of reactant. So our numerator is much, much greater than our denominator. And looking at HCl, we have 1.3 times 10 to the 6th to 1 is our ratio of product to reactant. This is 1,300,000. That means that there is 1,300,000 times more H pluses and Cl minuses than there are full HCl still stuck together. 1,000,000 times more. Sulfuric acid, H2SO4, it's only 1,000 times more. That's still way more. So these are strong acids. Their dissociation constants are larger than 1 because there's more ions than there are acid units still stuck together in the solution. Ivy might ask you for examples of strong acids. You're going to give them the examples of hydrochloric acid or sulfuric acid. Ivy might also ask you for examples of weak acids and bases. Examples are ethanoic acid. This can also be called acetic acid. This is basically vinegar. Carbonic acid, and then hydrosulfuric acid. Notice that their dissociation constants are much less than 1. And this is because there's only a tiny little bit of product. There is mostly still reactant. The denominator is much, much greater than is the numerator. There's way more of these acid units still stuck together. Only tiny little bits have popped apart or dissociated. So for ethanoic acid, acetic acid, we have 1.8 to 10 to the 5, 10 to the 5, 1, 2, 3, 4, 5, 100,000 ethanoic acid units still stuck together for every 1.8. We can round that to 2 that is popped apart into H pluses and that acetate ion. So we have way more acid units still stuck together, far fewer have popped apart. So how do we know if something is a weak acid? It has a dissociation constant much less than 1 because it has not dissociated much at all. Interestingly, strong acids have conjugate bases that are rather weak. This actually does make a lot of sense though. So HCl is a very strong acid. Most of it is going to pop apart into H pluses and Cl minuses. Tiny little bits might pop back together into HCls. Only very, very, very infrequently, right, 1 in a million times, is that Cl minus going to be a good acceptor of protons. Only every once in a while is it going to act as a base and turn back into HCl. So this guy, very strong. We're going that way most of the time. It is very uncommon for it to go backwards. So the Cl- chloride ion acting as a proton acceptor, not super strong. It is a very weak base. NH3 ammonia is a weak base. So sometimes it'll grab onto an H+, but not very often. Most of the time, ammonium is going to release that H+ and turn into H+ and ammonia. This is much more common because this acid, the conjugate acid of the ammonia base, is a much stronger acid. So a weak base is going to have a strong conjugate acid. A strong base would have a weak conjugate acid. Same thing for our acids. And it's all about that balance of donating or accepting those protons. So an interesting conceptual piece that we need to keep in mind in chemistry is that dilute acids and bases are not weak. HCl is a strong acid. It is always a strong acid because it always is going to almost completely dissociate in water. I can have a very unconcentrated, a dilute version of hydrochloric acid. Its pH is going to be, in this instance, because this is 1, 2, 3, 4, 5. This is a pH of 5. That feels like a weak acid, but it's not a weak acid. It's just a dilute acid. Hydrochloric acid is always a strong acid, but sometimes it's dilute. Same thing for ethanoic acid or acetic acid. It's always a weak acid, but sometimes it can be concentrated and therefore quite dangerous, but it's still weak, just concentrated. So be super careful, the difference between strong and weak and concentrated and dilute. Last slide of the lecture. How do I know? How can I test to determine if an acid is strong or weak? First up, conductivity. So we can plop electrodes attached to a light bulb into an acid. This is ethanoic acid. It is weak. Notice that there is barely any light at all. It's because this guy is going to dissociate into only a few tiny little pieces of H+ and those acetate ions, which means that there are not a lot of ions available to conduct electricity in the solution. However, HCl is a strong acid. We're going to have so many H+ and Cl- here in this solution, lots of ions to conduct the electricity in the solution. So we're going to have this crazy bright light bulb. Strong acids will have high conductivities. Weak acids do not have high conductivities. We can also neutralize acids and bases and then measure the enthalpy or the change in heat energy. So the stronger the acid and the base, the more energy will be released. That negative delta H means that energy is being released. This is going to feel warm. The temperature is going to rise because of the release of that energy, that enthalpy change. If I am neutralizing weak acids and bases, we're going to have a lower amount of heat energy propagated. It's not going to get as warm. And that, my friends, is our day. We did it in under 10 minutes. We talked about how pH is all about concentration, the concentration of those hydrogen ions, but the strength is all about that dissociation, that ratio of how many H+ and anions we have in relation to the acid molecules that are still stuck in units. We define strong and weak acids and bases. Strong acids dissociate a lot, weak acids do not. We talked about the strength in terms of those Ka's, that ratio of the ions to the acid units that are still stuck together. We understand that strong acids have weak conjugate bases. We talked about weak versus dilute acids and bases. Then we talked about those methods for determining if we've got a strong acid. We can look at its conductivity. We can also look at the delta H of the neutralization. How hot did that reaction get? Good work.